In this videotape, we will be concerned with solving systems of linear equations. In particular, we will be concerned with the case of solving two equations in two variables, or two unknowns. Okay? Let's consider this problem. X plus y equals 5. X minus y equals 1. Here we have a system of equations. We have two equations in two variables, or two unknowns, x and y. We are interested in solving this system of equations. That is, we are interested in finding out, are there any pairs of x and y values that satisfy both of these equations at the same time? Now, this is an equation of a straight line, and so is this. They both come under the category ax plus by equals c, okay, which we know to be a linear equation, that is the equation of a straight line. Okay, a and b are assumed not to both be 0. Now, these are two straight lines, okay, and we're interested in finding out, are there any x and y values that satisfy both equations at the same time? Now, it's not very hard to find a pair of x and y values that satisfy, say, the first equation or the second. The trick is to find a pair that satisfies both simultaneously. For example, 4, 1. Obviously, 4, 1, x equals 4, y equals 1, is a point which satisfies the first equation. If x equals 4 and y equals 1, 4 plus 1 is equal to 5. It does not, however, satisfy the second. 4 minus 1 is not equal to 1. Okay, 6, 5 is a point on the second equation. 6 minus 5, x minus y, 6 minus 5 does equal 1. It does not satisfy the first equation. 6 plus 5 is obviously not equal to 5. Okay, now we want to know, are there any points, okay, any pairs of values, x and y, that satisfy both equations at the same time? Now, we realize that the graph of this equation is a straight line and the graph of this equation is a straight line. So geometrically, we are looking at, okay, the graphs of two straight lines. We would like to know, are there any points in common, okay, for both of these equations? Now, if you have two straight lines, there are three possibilities geometrically. The two lines might be parallel. They might intersect at one point. Or the two lines might be coincident. Okay, they coincide there. One line actually falls right on top of the other line. There are three possible situations when you're talking about two straight lines. Okay, now, if we are interested in determining whether there are any solutions, okay, which satisfy both of these equations at the same time, that means we are looking for a point which simultaneously is on a point that's on both of these lines at the same time. All right, remember, if we have an equation of a line, every point on this line its coordinates must satisfy the equation of that line. Similarly, if we have a line here, every point on this line, its coordinates must satisfy the equation of this line. So where the two lines intersect, this point is on both of the lines. Its coordinates must satisfy both equations at the same time, and this would be a solution. If you're lucky enough to have a situation where the two lines intersect, okay, in one point, then you would have a solution to this problem. Okay, this is a case where we'd have one solution. On the other hand, if the two lines are parallel, we see that there are no points in common. Okay, the two lines do not cross, they do not intersect. Okay, there is never a time where there is a point on this line or a point on that line at the same time. Okay, they do not intersect, they have no points in common. If the lines are parallel, okay, there will be no solution to the problem. On the other hand, if the two lines are coincident, if one line exactly falls on top of the other line, then every point on the line satisfies both equations. It's on both of the lines. Every point on the line is a point of intersection, and there would be an infinite number of solutions. Okay? You can have, therefore, three possibilities. Okay? One of three possibilities. You have two linear equations. Okay, the graphs may intersect at one spot. This is the one we like the most. Okay, if they intersect the two straight lines, we will have one solution, a unique solution to the system of equations. If the lines are parallel, there will be no solution. If the lines fall on top of each other, if they're coincident, there'll be an infinite number of solutions to the system of equations. Okay, now how are we going to go about finding which one of these three categories this particular problem falls in? Okay, there are two ways of solving this system of equations. One way is to solve it geometrically. Okay, let's go over to the sideboard, and I will describe the geometric solution. Okay, we have the two equations, x plus y equals 5 and x minus y equals 1. We would like to solve them simultaneously. Okay, what I'm going to do is to graph each of the equations separately. And then I'm going to superimpose the two graphs, okay, and look to see if the lines have any points in common. X plus y equals 5, of course, is the equation of a straight line. And we make a little table of values. We have if x equals 0, if x equals 0, y equals 5. On the other hand, if y equals 0, x equals 5. And then just picking an arbitrary point to check. If x equals 1, 1 plus y equals 5, y must be equal to 4. So here are 3 points that lie on the first straight line. And plotting these points, we have 0, 5. X is 0. We don't move to the left or right. Y is 5. We move up 5 units. 5, 0. We move to the right 5, not up or down. So we're on the x-axis. We connect those 2 points. We get this straight line. And then we check by seeing that the point 1, 4, our third point, is on that line as well. This is the graph of the equation x plus y equals 5. Now let's look at the second equation. X minus y equals 1. Setting x equal to 0, if x equals 0, we get minus y equals 1. Dividing both sides by minus 1, y equals minus 1. If we let y equal 0, if y equals 0, x equals 1. And just picking another set of points, if another pair here of x and y values, if x equals 2, y equals 1, 2 minus 1 equals 1. And that's another pair of numbers that satisfy the equation. Now, let's plot them. 0 minus 1. Okay, you stay at the origin, you go down 1. 1, 0. You move to the right 1, not up or down. You stay on the x-axis. Connecting those 2 points, we get the straight line. And then we check and we see 2, 1, okay, lies on that line. So we have now the graph of the first straight line, the graph of the first equation, the graph of the second equation. Now, if we were to have drawn these two equations on the same set of axes, okay, I've done that over here. I've put both of these two equations, graphed both equations on the same set of axes. We see we have a case where the two lines intersect at one and only one spot here. Okay, this that you can read from the graph, this point has coordinates 3, 2. That is 3 over, 2 up. This is the common solution. 3, 2 is a point on the equation 3 minus y, x minus y equals 1, because 3 minus 2 is equal to 1. It is also a point on x plus y equals 5, because 3 plus 2 equals 5. It is a point on both equations, it's a point that satisfies both equations. Therefore, it is the solution to the system of equations here. It is also the only solution. We see that they intersect at one and only one spot, and since this point is on both of these equations, this must be the point 3, 2. It's the solution to this system of equations. And of course, you can always check by going back. 3 plus 2 equals 5, 3 minus 2 equals 1. Okay, now there are certain drawbacks to the geometric solution. Okay, when you're solving a problem geometrically, it's rather inefficient. And also, if you remember our work when we were solving it geometrically, it's sort of hard to read the answer. If you're lucky enough to have an integer answer, fine. you may be able to pick it off exactly. But if the answer, instead of being 3, 2, had been 3.1, 1.9, it would be very hard to read that accurately. Okay, so instead of solving a system of equations geometrically, we would prefer to solve it algebraically using the method of elimination. Okay. There are other ways, but we will be concentrating in this videotape on solving this system using the method of elimination. Okay, the whole idea in the method of elimination is that we're going to try to eliminate one of the variables in the problem and reduce it to a problem where there is one equation and one unknown, which we all know how to solve. We are going to assume when we have a system of equations that there is only one solution. Okay, if it turns out that there is more than one solution, this will become apparent as we work out the problem. It's the same thing when you want to work it out geometrically. You assume that they're going to intersect. If it turns out that there's no intersection, or if the two lines fall on top of each other, this would be apparent when you make your graph. The same thing in the algebraic solution. We're going under the assumption that there'll be one and only one solution. If either of these two situations arise, it will become apparent when we work it out. Okay. Now, to use the method of elimination, we have to recall the properties of equality. And what we're going to do here is assume, well, we have x plus y equals 5, x minus y equals 1. We're going to assume that there is a pair of values, x and y, that make both of these true at the same time. Okay, if that's the case, this is equal to this. Now, we know we can add equals. We can add the same quantity to both sides of an equation. So if we have x plus y equals 5 and x minus y equals 1, we can add x minus y to the left side here and 1 to the right side. That is, we can add the equations and still get an equivalent equation, assuming, of course, that these two equations could be solved simultaneously. Okay, let's do that. Let's add the equations. In doing that, notice that we get x plus x, 2x, plus y minus y, the y's drop out, 2x is equal to 6. Okay, we've got down equivalent, we have an equation, 2x equals 6, okay, which has only one variable. If we divide both sides by 2, we get x equals 3. Okay, having found x equals 3, we now go back to either of the two equations, either the first or the second, substitute in the value for x that we have found, solve for y, and it won't matter which one you use, and we will get the solution to the system of equations. Okay, let's say we try the first one. X plus y equals 5. If we let x equals 3, we have 3 plus y equals 5. Subtracting 3 from both sides, okay, we get y equals 2. So the solution to this problem, and we see we get the same answer that we got geometrically, the solution is x equals 3, y equals 2. Or you can write it this way, 3, 2. This is x equals 3, y equals 2 is the only solution to this problem. And of course, you can check always by going back to the equations. 3 plus 2 equals 5, 3 minus 2 equals 1. Now, this was a particularly simple problem, okay, because when we added the two equations, the y's dropped out. We're not always that lucky, okay, but there's always something that we can do to eliminate one of the variables. Let's consider another problem. 3x plus 2y equals 4, 2x minus y equals 5. Here we have a system of equations. We would like to solve it simultaneously. Okay, so what we're going to do is to use another property of equality, that we can multiply both sides of an equation by the same number. Okay, that's perfectly all right. What we're going to do is first of all, we'll decide what variable we're going to eliminate. Let's say we want to eliminate y again. We'll do a problem where we eliminate x after this. Okay, we want to eliminate y. The coefficient of y here is plus 2. Here it's minus 1. We would like to multiply, well, we could leave the first equation alone in this particular instance, multiply both sides of the second equation by 2. this would give us 4x minus 2y equals 10. Okay, we are allowed to multiply both sides of an equation by the number 2. There wouldn't be any problem in doing that, but when you do that, we'd get an equivalent equation here, and when you add that equation to the 3x plus 2y equals 4, the y's would drop out. Okay, the first equation I'm going to leave alone. Okay, in the second equation I'm going to multiply both sides by 2. This would give me 4x, and don't forget to distribute the 2 all the way through. 4x minus 2y is equal to 10. Now, the whole idea is that the coefficients of y are 2 and minus 2. In other words, they have, well, they're the same except for the sign, so that when we add them, they'll drop out. When we add, we get 7x. Now the y's drop out, equals 14. Dividing both sides by 7, x equals 2. Having found the value for x, we can now substitute into either equation. And doing so, we can find the value for y. Let's say last time we substituted into the first, we can substitute into the second. 2x minus y equals 5. X equals 2. 2 times 2 minus y equals 5. 4 minus y equals 5. Subtracting 4 from both sides. Minus y equals 1. Y equals minus 1. X equals 2. Y equals minus 1 is the solution here. Solution x equals 2. Y equals minus 1. And you can check it. Going back to the original equations, if we let x equals 2 and y equals minus 1, we should get both of these to be true statements. X equals 2, 3 times 2, that's 6. Minus 2 is equal to 4. And in the second, x equals 2, 2 times 2, 4. Minus 1 times minus 1, 4 plus 1 is equal to 5. And you should always go back and check your answers. Okay, now in this particular problem, we were sort of lucky because, well, the first was the easiest. We didn't have to do anything. We just add the equations and one of the variables dropped out. In the second one, okay, we only had to work on one of the equations. Okay, we multiplied the second equation by 2, and then we added the equations, and the y's dropped out. Okay, sometimes, however, you have to work on both of the equations. Okay, let's consider a problem like that. 5x minus 3y equals 9. 3x minus 2y equals 6. Okay, let's say we want to get rid of the, well, first of all, if we add the equations, nothing drops out. We get 8x minus 5y equals 15, which doesn't really help. Okay, we're going to have to, in this particular problem, multiply the top equation by something and also multiply the bottom equation by something, so that eventually when we add, one of the variables will drop out. Now you can choose to eliminate either of the variables. Okay, the work is about the same in this case. We can multiply the top equation by 3 and the bottom equation by minus 5. If we did that, this would be 15x, this would be minus 15x. When we add, the x's would drop out. We could also say multiply the top equation by 2 and the bottom equation by minus 3. This would give you a minus 6y here and a plus 6y here, and the y's would drop out. Okay, let's work on the x's in this particular one. Going to multiply the top equation, multiply by 3, and the bottom equation we're going to multiply by minus 5. Okay, if we multiply the top equation by 3, and remember we're distributing the 3 all the way through, we would get 15x minus 9y equals 27. And on the multiplying the bottom equation by minus 5, we get minus 15x plus 10y equals minus 30. Okay, let's look that over. We are multiplying the top equation by 3. The 3 is going to be distributed all the way through. 3 times 5, 15x minus 9y equals 27. We're multiplying the bottom equation by minus 5. Minus 15x plus 10y equals minus 30. Now, when we add the two equations, the x's drop out. Minus 9y plus 10y, that's y, equals minus 3. Now we go back to either of the two equations. Okay, let's say we substitute into the second equation. 3x minus 2y equals 6. We substitute in the value y equals minus 3. We get 3x minus 2 times minus 3 equals 6. 3x plus 6 equals 6. Okay, if we subtract, don't forget minus 2 times minus 3 is plus 6. If we subtract 6 from both sides, we get 3x equals 0. Dividing both sides of this equation by 3, we get x equals 0. Okay, 0 divided by 3, that's perfectly okay. That answer is 0. So x equals 0, y equals minus 3 is the solution that we find. X equals 0, y equals minus 3. And of course, we can check it by substituting back in. X equals 0, we get 0 minus 3 times minus 3, because y is minus 3, that's plus 9, that equals 9. And of course, in this one, 3 times 0 minus 2 times minus 3, that's plus 6, equals 6. Okay, and don't forget, you could have done this by eliminating y. You could have multiplied the top equation, say, by 2, the bottom equation by minus 3, giving you minus 6y and plus 6y. So when you add the equations, the y's would have dropped out instead of the x's. Okay, now so far, all of the problems that we have worked out had one solution, a unique solution. The two lines did in fact intersect. There was one solution, okay, and we were able to find it. Now remember, there was geometrically two other possibilities. The two lines could be parallel, in which case there would be no solutions, or the two lines could be coincident, in which case there would be an infinite number of solutions. Okay, it would be interesting to see how this would present itself to us algebraically. Let's work out this problem. We want to try to solve simultaneously x plus y equals 8 and 2x plus 2y equals 9. All right, we would proceed exactly in the same fashion. In this particular problem, we'd see it's enough to work on the top equation. If we multiplied the top equation by minus 2. Okay, if we multiply the top equation by minus 2, that is, we distribute the minus 2 all the way through, we get minus 2x minus 2y equals minus 16. The bottom equation we would leave alone, 2x plus 2y equals 9. Then when we add the equations, not only have we eliminated the x, but we've also eliminated the y. We have 0 plus 0, just 0 on the left, equals, adding the equations, minus 7. Now we all know 0 does not equal minus 7. We have here a contradiction. This means that our original assumption that the system of equations could be solved simultaneously was incorrect. Okay, we were acting like both of these equations could hold true at the same time. We worked on that premise. We added the equations. We got a contradiction. 0 equal to minus 7, which means our original assumption is incorrect. The two equations could not be solved simultaneously because these lines are parallel. Okay? If they're parallel, we know that there is no point in common for the two lines. The contradiction in this case means the lines can't be solved simultaneously. The equations can't be solved simultaneously. There are no points in common. There is no solution to this problem. Okay, geometrically, the lines are parallel. So if you get a contradiction, okay, a ridiculous statement like 0 equals 5 or something like that, this contradiction implies that the lines are parallel, that there is no solution for the system of equations. Let's say we want to solve simultaneously 4x plus 3y equals 2, 12x plus 9y equals 6. 4x plus 3y equals 2, 12x plus 9y equals 6. Okay, let's say we want to eliminate the x. Let's multiply the top equation by minus 3. If we do that, we get minus 12x minus 9y equals minus 6. The bottom equation we leave alone, 12x plus 9y equals plus 6. When we add, we find that the x's are eliminated, the y's are eliminated. We add, we get 0 on the left, and we also get 0 on the right. Okay, this reduces to the identity 0 equals 0. And this implies that there are an infinite number of solutions to the system of equations. That this line and this line, if you were to graph them, they're really the same line. Okay, they're coincident. Okay, if you notice, the second equation happens to be a multiple of the first. Okay, if you multiply the first equation by plus 3, we get exactly the second equation. The second equation is a multiple of the first. Every solution to the second equation is also a solution to the first. Every solution to the first equation is also a solution to the second. Okay, they're really the same line graphically. Any point which satisfies either of the equations is a solution to the system. 0 equals 0 means an infinite number of solutions to this problem. Okay, so in either of the two cases, okay, if we know the case, what it's going to look like when the two lines intersect at one point. Okay, then we get a nice set of value, x equals something, y equals something. The other two cases, either the lines are coincident or parallel. Either case, when you do your multiplication, you add, the whole left side drops out. The difference here is when there is an infinite number of solutions, the right side also drops out. You get 0 equals 0. When the lines are parallel, the left side drops out, the right side does not drop out. We get a contradiction. This implies that there is no solution. And that brings us to the end of the tape.